Welcome to the final Further Mechanics 1 video on Chapter 3. So in the last video we looked at elastic energy, and now we're going to use that with problems involving energies. So this is an extension from Chapter 2 again, whereas before in the AS part of the course we were just looking at gravitational potential energy and kinetic energy. We now have elastic energy into the mix as well. So we're going to look at 3 examples, and once we've gone through these you should then be fine to complete the final exercise 3D and the mixed exercise. So the first example, 13, we have a particle of mass 0.5 kilograms attached to one end of an elastic string. Always worth noting, obviously, in each question again whether we've got a string or a spring, of natural length 2 meters. So if we just list what we're told here, and modulus of elasticity is 19.6 newtons. Now the other end of the elastic string is attached to a point O, so actually I'll mark that as O instead. The particle is released from the point O here. Find the greatest distance it will reach below 0. So the greatest distance it will reach is the point at which it stops again. So we're going to look here at the distance it takes before it comes to 0. So if we want to think of this as the natural length of 2 meters, and there will be some extension on the string, obviously it will go through, and the velocity created there is going to stretch the string down further until it momentarily stops, and at that point it will obviously spring back again. So I'm going to set up the examples as I would for every question. This one is simpler, but I'm going to look at the total energy at O, and then if we call this point down here Y, we're going to look at the total energy at Y. Now I just get into the habit, because then it's the same thing every time you do a question. At O, we're going to look at kinetic energy, gravitational potential energy, and elastic potential energy. And at Y, we will do exactly the same. So kinetic energy, gravitational potential energy, and elastic potential energy. Now, it is released from rest. So it doesn't say released from rest, but if it's released, that means you're dropping it. You're not throwing it down with a velocity. So we know straight away our kinetic energy at this point is 0. It's a string, so it's not compressed. The string will just be loose there. So there is no elastic potential energy. And the gravitational potential energy, I always set my datum level at the bottom of the question, just like we did in Chapter 2. So therefore we have M, which is 0.5 G, and then H is going to be 2 plus X. Then if we consider all of the energies at Y, so it momentarily stops, so kinetic energy is 0, gravitational potential energy is 0, and elastic potential energy is going to be lambda, which is 19.6, multiplied by X squared, divided by 2 lots of L, which is 4. Now in the book it says the gravitational potential energy lost equals the energy gained. That is correct for this question. Okay, the elastic potential energy gained in the string, but I would just say the total energy at O is going to equal the total energy at Y, because there is no work done by any external forces. Okay, remembering that the weight, if I just put that there for the sake of argument, there will be a tension in the string. Okay, the weight is all tied into gravitational potential energy. So because there's no work done by an external force, we know the total energies at O and Y will be conserved. So we just have that 0.5 G 2 plus X is going to equal 19.6 X squared over 4. And we can see we can set up a quadratic there. That's going to end up being x squared minus x minus 2 equals 0 when we just do our rearranging. So therefore x is going to equal 2 or minus 1. So in this case we can ignore the extension being minus 1. It will be the positive value there, and it actually asks for the distance below O. So if the extension in the string is 2 meters, then we can see that the distance below O is going to equal 2 plus 2, which is 4 meters. So again, this is the method I tend to use. I think it's simpler because then you're doing the same thing every time and you're not worrying about when we've got 3 lots of energy. I think it's a bit clearer about the loss equaling the gain somewhere else if we just do it in that way. So consider your 2 points, total energies at one, total energies at the other, and then we can work things through from there. If we move on to example 14 now, so this time we have an elastic spring of natural length 1 metre, and modulus of elasticity is 10 newtons. So natural length is 1 metre and the modulus of elasticity is 10. Has one end attached to a fixed point A. A particle of mass 2 kilograms is attached to the other end of the spring and is held at the point B. Okay, now it says the particle is projected vertically downwards. So this time, unlike this question where it was released, this time it's actually projected downwards. So it has an initial velocity there of 2 meters per second. And we need to find the distance it travels before it comes to rest. So if we call that point C, so it's projected down and eventually comes to rest there. And obviously what would happen again is that it would reverse, change direction, spring back. Okay, so same thing again. Okay, we are going to look first of all at the energy at B, and we're going to look at the energy at C at the bottom there. I'm going to again take that as where I judge my, sorry, the red pen's run out again. So we're going to take the datum level at the bottom of the question. So if we look at all of those energies first of all, the kinetic energy at B is going to be a half of m, and the mass was 2 kilograms. I didn't put that on the diagram. So a half of 2 times by 2 squared. Our gravitational potential energy. Now this is where we've just got to consider what we've got going on. Now the natural length of the spring was 1 metre. So if we think of that and break it down like this, we've obviously got an extra 0.2 metres before it gets to its natural length. Okay, and then if we say the extension there is x, and we can set up our equation now as we have there. So the gravitational potential will be m, which is 2g times by h, which on my diagram, the height above the datum level is going to be x plus 0.2. And we have our elastic potential energy. And this is where you've got to be careful again, because there is elastic potential energy because it's a spring. So it's been compressed by a distance of 0.2 meters. So we've got lambda, which is 10, times by 0.2 squared over 2 lots of the natural length of 1. So there are actually 3 lots of energy there. It's thrown down with a speed of 2 meters per second. It's compressed, so there is an elastic potential energy. And of course, we have our gravitational potential energy too. The energy at C is a little bit simpler. The kinetic energy is going to be 0. The gravitational potential energy is going to be 0. And we have our elastic potential energy. So from the natural length there, we can see we've got an extension of x. So we've got 10 lots of x squared over 2 lots of 1. So I just think that's a little bit simpler to do it that way again. There are no, there's no work done by any external forces again. Okay, so we have the total energy at B is going to equal the total energy at C. So we've got, if we simplify some of these things out, we can see that that one straight away is just going to be 4. So we've got 4 plus 2g lots of x plus 0.2 plus 5 lots of 0.2 squared, just simplifying the 10 divided by the 2, and that's going to equal 5 lots of x squared. So we've got a quadratic again that we can set up, and that ends up being 5x squared minus 19.6x minus 8.12. And as I'm just running out of space, if I just use the calculations that they have in the book, so that will equal 0, and we end up with the positive value of x is going to equal 4.3 or minus 0.38. So again, we can ignore the negative value. And the question is asking for the distance it travels before coming to rest. So we've got the 0.2 meters plus our extension. So the distance traveled is going to be the 4.3 plus the 0.2, which is 4.5 meters to two significant figures. Now it's important that we look at example 15 as well. The previous two examples we had a conservation of energy as there was no work done by any external forces. Here we have a rough plane, so this gives us a good example of what we do when there is work done by an external force. So what we have here, a light elastic spring again of length 0.5 meters and modulus of elasticity 10 newtons. Has one end attached to a point A on a rough horizontal plane. The other end is attached to a particle P of mass 0.8 kilograms. The coefficient of friction between the particle and the plane is 0.4. We're going to use that with our work done by the friction force in a moment. And the particle initially lies on the plane with AP at 0.5 meters. So that's interesting. So at the starting point here, there will be no elastic potential energy because that is the natural length of the spring. And it's projected with a speed of 2 meters per second. So similar to the last example, we need to find the distance moved by P before it comes to rest. So this one's a little bit simpler in terms of knocking things together because it is starting at the natural length. So we can just mark that as our extension in the spring, and eventually it's going to come to rest. And that will be when the speed is 0 meters per second. So if let's use P there and B. So the energy at P, and we're going to look at the energy in my diagram at B. Now we don't need to worry about gravitational potential energy here because everything is horizontal. So we don't need to worry about gravitational potential energy, but just to get into the habit, there's no harm in just considering it just to make sure you've got all of your options. So here the kinetic energy is going to be a half of 0.8 multiplied by 2 squared. And our elastic potential energy, as we said, is also 0 because it's at its natural length at its starting point. At the end, we've got kinetic energy equals 0, and our elastic potential energy is going to be lambda x squared over 2 lots of 0.5, so that's just going to be 10x squared. So we've got 0.4 times by 4, so that's going to equal 1.6 joules there. Now, 10x squared doesn't equal 1.6 joules here, because as we've said already, we are going to have, it's a rough plane, and our friction force is mu r. So, work done by friction. If you want to think of the forces on the ball, we have 0.8 g. So we have our reaction force, and our friction force is going to be mu times by r. So very simple, resolving vertically. We know that r is simply equal to 0.8 g. So therefore, our friction force is going to be at its maximum, which is why I wrote it as 0.4 r straight away. Is going to be 0.4 multiplied by 0.8 g. So the work done by that force, so 0.32 g, is going to be the force itself, so 0.23 g multiplied by the distance travelled, which will be x. Okay, and then we've just got to consider what does that do to our pot of energies. Well, if it's a work done by a friction force, then that's going to be taking energy at the pot. So our energy at the start minus the work done by the friction force is going to equal our energy at the end. So we're going to have the total energy at the start, which was 1.6, minus 0.32 g lots of x, which is the work done by the friction force, and that's going to equal our total energy at the end, which is 10x squared. So once again, we create a quadratic equation. So we've got 10x squared plus 0.32 g lots of x minus 1.6 is going to equal 0. And if we work those through, x is going to equal 0.27 or minus 0.59. Again, we can ignore the negative value. And this time it just says, if I just check the question very quickly, it says the distance moved by P, which is just the extension. So therefore the distance moved equals 0.27 meters. And that's all there is to it. So you can now go at exercise 3D and mixed exercise 3, and very best of luck. Obviously the mixed exercise involves the equations using Hooke's law as well as energy. So there's lots of past exam questions there for you to practice. Best of luck, everyone.